Okay, we'll both be on the same side. Solidarity. Yes, we're working on the ANITA and HiCal2 experiment. We're missing Sabrea and Roxanna. One is sick and one is looking at wedding dresses for her sister. So we are here today.
I'm Finn.
And I'm Asher.
And we're working on the ANITA and HiCal2 experiment. So ANITA stands for Antarctic Impulsive Transient Antenna. Its purpose is to detect cosmic rays over Antarctica. And it does it when cosmic ray protons enter the atmosphere. They collide with air molecules and create radio bursts that send radio frequencies down that reflect off the ice and then receive back up in the ANITA antennas. And if this floats about 35 kilometers in the air, it circles along a wind current above Antarctica. HiCal was first used with ANITA 3. It is a follower balloon. Its purpose was to test the reflectivity of the ice through direct and reflected signals to ANITA. It did it by using a piezo sparker, which is like a barbecue lighter, sent out a radio pulse that could be received by ANITA. It flies within 200 kilometers of ANITA, but can operate up to 700 kilometers away. Now, the problem with the HiCal was that the data, you can only get about 24 hours of usable data from 10 days of flight. That's just due to the limitations of battery power. And so that's where we came in. Our purpose this summer was to see how solar power could be used as an alternative to battery power.
So yeah, we had a launch with like a balloon carrying a payload and an antenna. So our main goals for that launch was one, to test solar panel reliability, which is referring to like the physical integrity of the solar panel. Because in tests they did, other labs did, the solar panels would go up, and it would get really cold, and then it would increase a lot in temperature. So the solar panels would like pop or whatever and stop supplying voltage to the electronic components of the payload. And then another is to check out the solar panel's variability in the voltage it's supplied. Like there's a range, and it can be anywhere within that range, but the data logger like records this, and from that we can infer like what the conditions are up there. Like how much of the solar panel is facing the sun, how much our payload gets jostled about. And so yeah, that was one of the things we were testing for the launch. And of course, to transmit and receive a signal at a distance, we had an antenna that transmitted to a ground station, and it had to be able to transmit like 20 kilometers based on the Antarctic experiment, like to emulate that.
This schematic and the pictures of the payload that we sent up earlier this month. You can see we sent up in the schematic, there's a data logger which records the voltage that the solar panel puts out. There's a GPS for tracking it, and then a VCO which converted the voltage into a radio frequency that was sent out through the antenna that we received on the ground. And so we'll go through the launch in the next few slides.
Okay, so this was our launch area. We went up to Shocky's farm, which is like by the pumpkin patch, and brought everything out there. This is the balloon fully inflated. This is our helium tank. We had to carry that out there, and like our antenna is right there, and the orange thing is the parachute, which was then launched. This is Connor Brown holding our payload. There's the antenna on the ground. So yeah, there were some issues with the launch. Right here, that's Connor and Roxanna saving data. The tarp was pulled over, like partially because it was really hot, but mainly so that you could see the screen. Because the sun. So like the data was saved. Like the signal comes in from our antenna that's on the balloon into the antenna, which is then taken to the oscilloscope, which gives like a waveform. So then they're saving that onto floppy disks, but the issue was that it would save the same waveform like multiple times over a period of time, like the oscilloscope had frozen or something like that. So there wasn't like a lot of reliable data for a lot of the flight. And then also GPS tracking was an issue because the GPS on the balloon's way down, the GPS stopped working at about 1,000 feet. Or was it 1,000 or 10,000? 10,000 feet in the air. So from there, like we had a trajectory of where it's going to go, and had that GPS point when it was above 10,000 feet. But so like we knew a general area of where it landed, but we didn't have the specific thing because it wasn't giving us a GPS location on the ground. So we weren't able to recover the entire flight. So we didn't like receive any, or we don't have the data from the flight. Assuming that the data logger successfully worked to record the voltages. So yeah, in the future there will be another flight. This flight will also have it be powered. The electronic components of the flight will be powered by a solar panel, which will be connected to another data logger, so we can basically redo that whole section. And then the balloon will be larger, so they can carry a larger payload. But hopefully the flight will be about the same time span. And then we'll have a pressure vessel with a sparking mechanism, like a piezo inside the pressure vessel. And then we'll have tracking, like high altitude and low altitude tracking. So the high altitude will just be GPS, like we had before. And then we'll have low altitude using GSM networks. So it'll basically be like Find My iPhone or whatever, to give us like an exact location of where it is on the ground, so we can make sure to recover all of our equipment and data from the equipment. Some credits. Special thanks to Connor, Josh, and Dave for making everything work.
Okay, are there any questions?
Yeah, we don't have the questions then. Yeah.
So did you put a solar panel up, or you didn't put a solar panel?
We did.
Okay, and so how do you know what direction it was facing?
Well, we would be able to get a general sense of that if we had the data logger, which records the voltages. But since we couldn't retrieve the data logger, we really have no clue.
How big was your solar panel?
So that big.
Yeah.
Okay.
So how big was your search area? Like where could your package, your data logger package be right now?
I don't know the dimensions of the area. Do you have an idea, Connor, of the?
Maybe a square mile.
Yeah. And there are a lot of trees out there, and also open fields. So hopefully, yeah.
Do you know anybody with a good drone who could do a little flyover? Seriously, if you had an orange parachute.
We've already been over that.
Yeah.
We were out to get a drone to do it, but the drone person fell through because their drone broke.
Yeah, they crashed it into a lake the weekend before we were going to use it that Monday.
That was rude.
So did you have to get any special permission to let a balloon go up to 10,000 feet?
We contacted like the airport, and I think some other authority maybe, but yeah.
What was the maximum altitude that you expected your balloon to go up to?
I'm going to interject here. I'm sorry I didn't get you guys any data for this. We did get some retrievable data from this, from the GPS track, because it was live updating on the website that we could follow it. And it did end up going to a little over 33 kilometers up in altitude. And we were able to derive its ascent rate, its descent rate, its position. We got some useful data out of it. Just, sorry, I wasn't aware you guys were presenting today, otherwise I'd actually throw it in here to present. But so it wasn't like a total wash. We did get some data out of this. We did learn its burst altitude and some other things.